In mathematics, the natural numbers are those used for counting and ordering. In common language, words used for counting are cardinal numbers, and words used for ordering are ordinal numbers. Some authors begin the natural numbers with 0, corresponding to the non-negative integers 0, 1, 2, 3, whereas others start with 1, corresponding to the positive integers 1, 2, 3. Texts that exclude 0 from the natural numbers sometimes refer to the natural numbers together with 0 as the whole numbers, but in other writings, that term is used instead for the integers. The natural numbers are the basis from which many other number sets may be built by extension. The integers, by including an additive inverse for each natural number n. The rational numbers, by including a multiplicative inverse for each integer number n. The real numbers, by including with the rationals the Cauchy sequences of rationals. The complex numbers, by including with the real numbers the unresolved square root of -1, and so on. These chains of extensions make the natural numbers canonically embedded in the other number systems. Properties of the natural numbers, such as divisibility and the distribution of prime numbers, are studied in number theory. Problems concerning counting and ordering, such as partitioning and enumerations, are studied in combinatorics. In common language, for example in primary school, natural numbers may be called counting numbers to contrast the discreteness of counting to the continuity of measurement established by the real numbers. The natural numbers can, at times, appear as a convenient set of names, that is, as what linguists call nominal numbers, foregoing many or all of the properties of being a number in a mathematical sense. History. Ancient roots. The most primitive method of representing a natural number is to put down a mark for each object. Later, a set of objects could be tested for equality, excess or shortage, by striking out a mark and removing an object from the set. The first major advance in abstraction was the use of numerals to represent numbers. This allowed systems to be developed for recording large numbers. The ancient Egyptians developed a powerful system of numerals with distinct hieroglyphs for 1, 10, and all the powers of 10 up to over 1 million. A stone carving from Karnak, dating from around 1500 BC and now at the Louvre in Paris, depicts 276 as 200s, 7 10s, and 6 1s, and similarly for the number 4622. The Babylonians had a place value system based essentially on the numerals for 1 and 10, using base 60, so that the symbol for 60 was the same as the symbol for 1, its value being determined from context. A much later advance was the development of the idea that 0 can be considered as a number, with its own numeral. The use of a zero digit in place value notation dates back as early as 700 BC by the Babylonians, but they omitted such a digit when it would have been the last symbol in the number. The Olmec and Maya civilizations used 0 as a separate number as early as the 1st century BC, but this usage did not spread beyond Mesoamerica. The use of a numeral 0 in modern times originated with the Indian mathematician Brahmagupta in 628. However, 0 had been used as a number in the medieval computus, beginning with Dionysius Exiguus in 525, without being denoted by a numeral. Instead, nulla from nullus, the Latin word for none, was employed to denote a zero value. The first systematic study of numbers as abstractions is usually credited to the Greek philosophers Pythagoras and Archimedes. Some Greek mathematicians treated the number 1 differently than larger numbers, sometimes even not as a number at all. Independent studies also occurred at around the same time in India, China, and Mesoamerica. Modern definitions in 19th-century Europe, there was mathematical and philosophical discussion about the exact nature of the natural numbers. A school of naturalism stated that the natural numbers were a direct consequence of the human psyche. Henry Poincaré was one of its advocates, as was Leopold Kronecker, who summarized God made the integers, all else is the work of man. In opposition to the naturalists, the constructivists saw a need to improve the logical rigor in the foundations of mathematics. In the 1860s, Hermann Grassmann suggested a recursive definition for natural numbers, thus stating they were not really natural but a consequence of definitions. Later, two classes of such formal definitions were constructed. Later, they were shown to be equivalent in most practical applications. Set theoretical definitions of natural numbers were initiated by Frege, and he initially defined a natural number as the class of all sets that are in one-to-one correspondence with a particular set. But this definition turned out to lead to paradoxes, including Russell's paradox. Therefore, this formalism was modified so that a natural number is defined as a particular set, and any set that can be put into one-to-one correspondence with that set is said to have that number of elements. The second class of definitions was introduced by Giuseppe Peano and is now called Peano Arithmetic. It is based on an axiomatization of the properties of ordinal numbers. Each natural number has a successor, and every non-zero natural number has a unique predecessor. Peano arithmetic is consistent with several weak systems of set theory. One such system is ZFC, with the axiom of infinity replaced by its negation. Theorems that can be proved in ZFC but cannot be proved using the Peano axioms include Goodstein's theorem. With all these definitions, it is convenient to include 0 as a natural number. Including 0 is now the common convention among set theorists and logicians. Other mathematicians also include 0, although many have kept the older tradition and take 1 to be the first natural number. Computer scientists often start from 0 when enumerating items like loop counters and string or array elements. Notation. Mathematicians use N to refer to the set of all natural numbers. This set is countably infinite. It is infinite but countable by definition. This is also expressed by saying that the cardinal number of the set is Aleph naught 0. To be unambiguous about whether 0 is included or not, sometimes an index 0 is added in the former case, and a superscript asterisk or subscript 1 is added in the latter case. 0 equals 0 equals 0, 1, 2, asterisk equals plus equals 1 equals greater than 0 equals 1, 2. Properties. Addition. One can recursively define an addition on the natural numbers by setting a plus 0 equals or and a plus s equals s for all a. Here s should be read as successo. This turns the natural numbers into a commutative monoid with identity element 0, the so-called free object with one generator. This monoid satisfies the cancellation property and can be embedded in a group. The smallest group containing the natural numbers is the integers. If one is defined as s, then b plus 1 equals b plus s equals s equals s. That is, b plus 1 is simply the successor of b. Multiplication. Analogously, given that addition has been defined, a multiplication times can be defined via a times 0 equals 0 and a times s equals plus a. This turns into a free commutative monoid with identity element 1. A generator set for this monoid is the set of prime numbers. Relationship between addition and multiplication. Addition and multiplication are compatible, which is expressed in the distribution law. A times equals plus. These properties of addition and multiplication make the natural numbers an instance of a commutative semi-ring. Semi-rings are an algebraic generalization of the natural numbers where multiplication is not necessarily commutative. The lack of additive inverses, which is equivalent to the fact that is not closed under subtraction, means that is not a ring, instead it is a semi-ring. If the natural numbers are taken as excluding 0 and starting at 1, the definitions of plus and times are as above, except that they begin with a plus 1 equals s and a times 1 equals a. Order in this section. Juxtaposed variables such as ab indicate the product a times b, and the standard order of operations is assumed. A total order on the natural numbers is defined by letting a be if and only if there exists another natural number c with a plus c equals b. This order is compatible with the arithmetical operations in the following sense. If a, b and c are natural numbers and a b, then a plus c b plus c and ac b c. An important property of the natural numbers is that they are well ordered. Every non-empty set of natural numbers has a least element. The rank among well-ordered sets is expressed by an ordinal number. For the natural numbers, this is expressed as omega. Division in this section. Juxtaposed variables such as ab indicate the product a times b, and the standard order of operations is assumed. While it is in general not possible to divide one natural number by another and get a natural number as a result, the procedure of division with remainder is available as a substitute. For any two natural numbers a and b with b0, there are natural numbers q and r such that a equals bq plus r and r less than b. The number q is called the quotient and r is called the remainder of division of a by b. The numbers q and r are uniquely determined by a and b. This Euclidean division is key to several other properties, algorithms, and ideas in number theory. Algebraic properties satisfied by the natural numbers. The addition and multiplication operations on natural numbers as defined above have several algebraic properties. Closure under addition and multiplication. For all natural numbers a and b, both a plus b and a times b are natural numbers. Associativity. For all natural numbers a, b, and c, a plus equals plus c and a times equals times c. Commutativity. For all natural numbers a and b, a plus b equals b plus a and a times b equals b times a. Existence of identity elements. For every natural number a plus 0 equals a and a times 1 equals a. Distributivity of multiplication over addition. For all natural numbers a, b, and c, a times equals plus. No non-zero zero divisors. If a and b are natural numbers such that a times b equals 0, then a equals 0 or b equals 0. Generalizations. Two generalizations of natural numbers arise from the two uses. A natural number can be used to express the size of a finite set. More generally, a cardinal number is a measure for the size of a set, also suitable for infinite sets. This refers to a concept of size, such that if there is a bijection between two sets, they have the same size. The set of natural numbers itself and any other countably infinite set has cardinality Aleph null. Linguistic ordinal numbers, first, second, third, can be assigned to the elements of a totally ordered finite set, and also to the elements of well-ordered countably infinite sets like the set of natural numbers itself. This can be generalized to ordinal numbers which describe the position of an element in a well-ordered set in general. An ordinal number is also used to describe the size of a well-ordered set, in a sense different from cardinality. If there is an order isomorphism between two well-ordered sets, they have the same ordinal number. The first ordinal number that is not a natural number is expressed as omega. This is also the ordinal number of the set of natural numbers itself. Many well-ordered sets with cardinal number 0 have an ordinal number greater than omega. The least ordinal of cardinality 0 is omega. For finite well-ordered sets, there is one-to-one correspondence between ordinal and cardinal numbers, therefore they can both be expressed by the same natural number, the number of elements of the set. This number can also be used to describe the position of an element in a larger finite, or an infinite, sequence. A countable non-standard model of arithmetic satisfying the Peano arithmetic was developed by Skolem in 1933. The hypernatural numbers are an uncountable model that can be constructed from the ordinary natural numbers via the ultra-power construction. Georges Reb used to claim provocatively that the naive integers don't fill up. Other generalizations are discussed in the article on numbers. Formal definitions. Peano axioms. Many properties of the natural numbers can be derived from the Peano axioms. Axiom 1. 0 is a natural number. Axiom 2. Every natural number has a successor. Axiom 3. 0 is not the successor of any natural number. Axiom 4. If the successor of x equals the successor of y, then x equals y. Axiom 5. If a statement is true of 0, and if the truth of that statement for a number implies its truth for the successor of that number, then the statement is true for every natural number. These are not the original axioms published by Peano, but are named in his honor. Some forms of the Peano axioms have 1 in place of 0. In ordinary arithmetic, the successor of x is x plus 1. Replacing axiom 5 by an axiom schema 1 obtains a first-order theory called Peano arithmetic. Constructions based on set theory. Von Neumann construction in the area of mathematics called set theory. A special case of the von Neumann ordinal construction defines the natural numbers as follows. Set 0 equals the empty set. Define S equals of A for every set A. S is the successor of A, and S is called the successor function. By the axiom of infinity, there exists a set which contains 0 and is closed under the successor function. Such sets are said to be inductive. The intersection of all such inductive sets is defined to be the set of natural numbers. It can be checked that the set of natural numbers satisfies the Peano axioms. It follows that each natural number is equal to the set of all natural numbers less than it. 0 equals 1 equals 0, 0 equals 0 equals 2 equals 1, 1 equals 0, 1 equals 3 equals 2, 2 equals 0, 1, 2 equals n equals n minus 1, n minus 1 equals 0, 1, n minus 1 equals, etc. With this definition, a natural number n is a particular set with n elements, and nm if and only if n is a subset of m. Also, with this definition, different possible interpretations of notations like n coincide. Even if one does not accept the axiom of infinity and therefore cannot accept that the set of all natural numbers exists, it is still possible to define any one of these sets. Other constructions. Although the standard construction is useful, it is not the only possible construction. Zermelo's construction goes as follows. Set 0 equals. Define S equals A. It then follows that 0 equals 1 equals 0 equals 2 equals 1 equals n equals n minus 1 equals, etc. Each natural number is then equal to the set of the natural number preceding it.